In this session, let's take a bit of a closer look. So we've looked at the overview before. Now let's look at a bit of a closer look. So data analytics has several kinds of characteristics. We're usually using quite large data sets. We're interested in discovering things that are not obvious. So if they're obvious, we can use maybe an SQL query just to find them. But here we're looking for things that are not really obvious. There's no specific hypothesis that we're interested in here. So in statistics, you usually have a hypothesis, you collect data, and then you see how that hypothesis, whether the data supports that hypothesis. With data mining, data analytics, there's no specific hypothesis. We're usually trying to find knowledge that can improve processes or make better decisions. It's generally impossible to do manually. You can't just look through these data sets and work it out yourself. And data analytics has a sort of a special characteristic where you're trying to get knowledge from data in any way that you can. There's not necessarily a fixed approach to solving problems. We're really using any tricks and tips that we can to work out how to find the knowledge. We often see something called the knowledge discovery process. It looks a bit like this. So we start with databases. We do some data cleaning and integration to get a data warehouse. We do some data selection to get the task relevant data, so the data that's going to be used for the particular task that we're interested in. Then we do our data mining where we're looking for patterns. We evaluate those patterns, and out of that comes knowledge. So you'll often see this kind of diagram. It always looks like we're heading up towards climbing up the mountain to get to the knowledge. And it seems like it's a waterfall process if you know about software engineering, but really it's not a waterfall process. It's really quite iterative. This is the knowledge discovery data. KDD is knowledge discovery in data sets. And there's a process. Again, this sort of is a little bit similar to what we've seen previously. We want to look at an application domain, look at our data selection. One thing I think is really important on this slide is that we need to do data cleaning and pre-processing. And this, even though it's sort of a bit boring, it can take up to 60% of the effort of the project. So out of your entire project, 60% of the time is just getting your data together, cleaning it and pre-processing it. Most of the time is not spent on building the models. We might do some data reduction and transformation. There's a thing called dimensionality reduction or feature subset selection. So we'll be looking at those kinds of things in a few weeks. And then we do our data mining. So we either do classification, regression, clustering, and then eventually we'll do some pattern evaluation and then use the data. This is just a couple of important rules. One is activity is not a substitute for thought, i.e. think about what you're doing before you do it. Ronnie Cahovey from Amazon, peel the onion. So he means look deeper and deeper into the problem as you peel off layers. And I guess my rule is think about what you're doing. Don't just automatically do things. Data analytics has borrowed from a whole lot of different areas: database technology, stats, AI, which we've seen a little bit already, visualization, information science, and other disciplines. So I just want to highlight some of those links in this next bit. First off, databases. So databases, there's a whole lot of different approaches. There's relational databases, transaction databases, and data warehouses, but there's a whole lot of advanced database systems. There's object relational databases, which are a bit old these days, but spatial databases that particularly work with time series or multimedia, and different kinds of databases. In terms of database technologies, data warehouses, which we've talked a little bit about already. So they're subject-oriented. They're integrating a whole lot of different data together. And they're a good place to start with our data mining. There's data marts, which are maybe a bit smaller, and then we can do the OLAP, which we talked about a little bit earlier. We can drill down on the data, we can roll it up, we can slice it into data cubes. Some vendors talk about OLAP ideas as being synonymous with data analytics or data science. Really, I think there's a bit of a difference. The OLAP is really the starting point for what we're going to do. So OLAP, the emphasis is on the query, so you know what you're going to look at. You know what you'd want to find. You can express the query in SQL or some kind of language like that, and you produce these data cubes. Data mining, on the other hand, there's more of an emphasis on exploration. Rather than a query where you know what you want, you're exploring. You don't really know what you want. You have a general idea of what you want, but you don't really know how to find it. And also you're letting the machine drive the exploration. So sometimes people talk about it as being a conversation with the data or dancing with the data. So from database technology, a whole lot of ideas have really become quite important in data analytics and AI. So first off, there's this idea of database design and modeling. So all the ideas of tables and schema, procedures, all of that kind of stuff has really been a big influencer in data analytics. Of course, there's the database interface to the data mining, getting our data. The databases are really good at importing and exporting data efficiently and partitioning data, tuning data, and the parallel processing. And the ideas of distributed information repositories. All of those ideas have really influenced data analytics quite a lot. In terms of statistics, a whole lot of ideas have really come from statistics into artificial intelligence and data analytics, and other things have flown back as well. First off, we've got things like data and counting. The idea of probabilities and hypothesis testing are really important ideas from statistics that are used in data analytics. The ideas of correlation and a lot of the regression methods have been really influential and are really good places to start in data analytics. There's a thing called exploratory data analysis by a statistician called John Tukey, and that's a very influential idea that has become part of data analytics. There's a whole lot of predictive models that have been developed in statistics schools that have eventually been used in data analytics. So for example, there's CART, classification and regression trees. These are one of the decision tree methods, and that was developed in a statistics school. There's MARS. There's a thing called TreeNet, which is a sort of a decision tree, ensemble decision tree method, which is a fantastic approach, again, coming from a statistics area. And then random forest, which we'll look at a little bit later in the semester, again, coming from a statistics background. So statistics really provide important foundations for what we can do in data mining and knowledge discovery. There's the ideas of sampling, probability, of course, and then all of these really new types of methods and very important methods that in data analytics called ensemble methods. So random forest and TreeNet are examples of those. Those methods, and ensemble methods, bagging and boosting in general, they have come from a statistics background. In terms of statistics, we can break it into descriptive statistics and predictive statistics. And again, this sort of mimics the idea of this unsupervised and the supervised learning a little bit as well. In terms of descriptive statistics, we're looking at the minimum, the maximum, the median, the mean, and we have summary statistics that can describe a whole group of data. In terms of the predictive statistics, we can use those to make forecasts and inferences. So for example, you can see there's two sample sets that are graphed below. So we can ask a question in statistics, are those two sample sets identically distributed? Statistics usually takes a hypothesis-driven process. So this little cartoon sort of shows how things fit together. So in statistics, you'll start with a hypothesis, and that comes from some kind of a priori knowledge. So in the first panel, we hypothesize that drinking beer makes people feel good, and that the more beer you drink, the better you feel. So you can see there's a graph of that. The next thing we do, we have our hypothesis, now we collect some data. So we make observations. And we can see there's a whole lot of data points of people, how they feel, and how many beers they've drunk. And you can see that it's made a kind of a pattern. So in statistics, we now compare the observed data with the hypothesized pattern, with the hypothesis, and then we conclude, and then we see whether the hypothesis is supported by that data. And we can see in this case that the hypothesis isn't supported by the data. So we would then need to revise the hypothesis and then go out and collect some more data. And you iterate through this until you've got a good model. So data mining and data analytics takes a slightly different approach. We start off with the data. So we observe how people feel, and then we do some analysis of that. So we might build a regression line, which is what that red part is, or we might do some clustering, which is what that blue circles are supposed to do. Regardless, we can identify that there's a pattern in the data, and you can see that line there in the middle panel. Then we can conclude, so we generalize from that shape to when we can conclude that people in general feel better when they drink more beer, but only up to a point. And after that point, people feel much, much worse. So usually the patterns are not that obvious, but this is sort of the schematic for how we go about solving these problems. Let's talk a little bit now about AI. So AI brings, the things that AI brings to data analytics is this inductive approach or machine learning. So all those ideas of machine learning, the supervised and unsupervised, they've come from AI. There's a whole lot of methods for knowledge representation that have come from AI, inference, and then coming back from data analytics back into AI. Often data analytics is used as components in multi-agent systems, for example, so it can make predictions that can then be exploited by the agent. So the artificial intelligence has taken this design, so the design cycle for predictive modeling has come from AI, and that's been used in data analytics. So the idea of collecting data, selecting the features, the model, training it, and then evaluating it, which we'll see quite a lot of this semester. Those ideas have come from AI. Visualization is an important aspect in data mining because we're trying to understand and see what's happening in the data. There's the idea of a picture being worth 1,000 words, and it's a really easy way for people to understand what's happening. So really it's used for understanding the data. And you can see the first picture there is a scatter plot. We'll be looking at those a little bit later. The second one you may not have come across. It's pretty cool. It's an idea called parallel coordinates, and it's a way of representing data. Each of the lines in that plot is one data point, and each of the points that it goes through is a value in that particular attribute. So you can see for the first one, it might be a bit hard to see, but the first one is horsepower. Second one is number of cylinders, so these are cars. The price point, the engine size, and then the fuel tank capacity. And you can see that there's clusters or groups of cars in particular ideas. So there's been a whole lot of approaches more recently from data analytics that have come from software engineering and gone into data analytics. So the idea of the CRISP-DM methodology, which I talked about earlier, those ideas have come, they're like software engineering practices. There's a whole lot of ideas of using XML and those kinds of architectures for transporting data have come into data analytics. So there's a thing called PMML, Prediction Model Markup Language, which is used for exporting models. There's this whole idea of using APIs to access data and models, so things like Weka, which is a Java machine learning toolkit. Orange is D3.js, which is a JavaScript library for doing visualization. The packages in Anaconda are also, they have an API into them and you can use them. And increasingly, there's a delivery of data analytics through web services. And increasingly, particularly with the deep learning neural networks, high performance computing has really contributed towards data analytics. And the ideas of big data with volume, velocity, and variety, which we've seen before, those ideas come from high performance computing and are used. And they're used to address the fact that algorithms are slow. We need to look at the computational complexity of algorithms and potentially use parallel algorithms when we can to solve problems.